Aloha, everyone. Welcome to Live from NOIRLab at Gemini. I'm Odysseus Quarles, a Gemma intern at the International Gemini Observatory here in Hilo, Hawaii. Now, before I introduce our guest today, remember if you have any questions or comments, please type them into the YouTube live chat box, and our moderator, Jamika Marshall, will read them out loud during the presentation. Joining me today is Dr. Michael H. Wong. Mike Wong is a research scientist at the Center for Integrative Planetary Science at UC Berkeley. He is on the science teams for NASA's Juno and Mars Science Laboratory missions. He co-founded the OPAL program of the Hubble Space Telescope, which takes annual images of all 4 giant planets. His main research is on cloud-forming gases in giant planet atmospheres, gases that also tell the story of the formation of the giant planets. He has used imaging and spectroscope remote sensing data from the ground and from spacecraft, as well as mass spectrometer data obtained directly in the atmospheres of Mars and Jupiter. Thanks for joining us today, Mike.
It's great to be here.
So, now before we let Mike take us on a journey to the biggest and stormiest planet in the solar system, let's talk a little bit about the Gemini Observatory. Gemini is a program of the National Science Foundation's NOIRLab. The name Gemini comes from the Latin word for twins and from the constellation of the same name, which depicts a pair of twins holding hands. Gemini is composed of 2 identical 8.1 meter telescopes, Gemini South in Chile, atop Cerro Patron alongside the Southern Astrophysical Research Telescope and the Vera C. Rubin Observatory, and Gemini North here on the Big Island of Hawaii, where it shares the summit of Mauna Kea with 13 other observatories at one of the best astrophysical observing sites in the world. Gemini is funded by the National Science Foundation and our 5 international partners: Argentina, Brazil, Canada, Chile, and South Korea. Researchers from the United States and our international partners are given observing time on the Gemini telescopes based on their nation's funding level. Now let's take a look inside the Gemini North Telescope. On the left, you can see the inside of the dome. That's what we call the huge building that is home to the telescope. The telescope is in the middle of the dome there. Now, some of you might have telescopes at home, and you might be thinking that this looks absolutely nothing like that. The primary mirror you can see is out in the air, and the secondary mirror is way up on a truss. Now, there are 2 big reasons for these differences. First, this lets cool night air pass freely through the telescope. That's also why the vents around the outside of the dome are open. Second, the dome already protects the telescope from the elements. Adding a tube to cover the mirrors would just add weight, meaning it would take more power to aim the telescope and make it harder to clean and do maintenance on the mirrors. The back of the telescope, which you can see here on the right, is where the science happens. Light bounces off the primary mirror, then off the secondary mirror, and then through the center of the telescope, where it goes to a beam splitter. The beam splitter sends some light to the adaptive optics system, which subtly adjusts the shape of the mirror to give the clearest, sharpest images possible. And the rest of the light goes to Gemini North's many detectors. Each detector takes images in a different part of the light spectrum, from visible light to infrared. One of these instruments, Gemini North's near-infrared imager, which we call NIRI, played a big role in the science Mike Wong is going to talk to us about today. But one last thing before we get started. We're happy to announce that Gemini North restarted observations last week on the night of May 19th. Following guidelines set by the state and federal governments regarding COVID-19, a minimal on-site crew resumed science operations. So a big thank you goes out to our night crew. For now, Gemini facilities remain closed to the public, and most of our staff, including myself and the rest of the Live from NOIRLab team, will continue to work from home to keep our observers and our community safe. In just a moment, I'll hand you over to Mike Wong for his presentation on Jupiter's lightning storms. But just before we start, I'd like to remind any new viewers that if you have any questions or comments, please type them in to the YouTube live chat, and our moderator, Jamika, will read them out loud during the presentation. Mike, thanks for joining us today. It's great to have you on.
Great, thank you. I'm glad to be here. I'm speaking to you today from San Francisco, where we're hopefully ending a little heat wave and we're still under shelter-in-place orders. So my observations with Gemini lately have focused on data taken with NIRI, as Odysseus introduced. And this image was released by the Gemini Public Information Office on May 7th. So I'm going to be talking today about the science behind this image and trying to address this question from the title slide: where does lightning come from on Jupiter? Now, unfortunately, I can't give you a complete answer at this time, but it's very exciting that with Gemini, Hubble, and the Juno spacecraft, as well as other observatories simultaneously looking at Jupiter, we now have one of the most comprehensive investigations of this question ever. So first of all, when we look at Jupiter with NIRI, for this experiment, we're using a wavelength of 4.7 microns. Now, this is in the thermal infrared, so we're seeing actual heat emission coming from Jupiter's atmosphere rather than what you would see with the eye, which is sunlight reflected back from the planet. So at this wavelength of 4.7 microns, Jupiter is shining from its own light, its own heat. And all the dark regions that you see in the image, those are very cloudy regions. And the bright regions are clearings. So as with the Earth's atmosphere, the cloudy part of Jupiter's atmosphere, it's called the troposphere, and the temperature goes up and up the deeper you go in. So anywhere you can see deep into the atmosphere, these clearings, you're gonna see warmer regions, they emit more in the infrared, and anywhere where it's dark, that's because the clouds are blocking your view. You're only seeing the shallower regions that are very cold. So this spectacular image is one example of our data sets. And here you don't see the great red spot, but I'll show you another picture that does have the great red spot. Before we get to that, I wanna go over this technique we use called lucky imaging. And now it's been called the most powerful imaging technique in the press release, but in some ways it's very simple. And a lot of people use this technique also at visible wavelengths. Amateur astronomers often record video of their targets and then select out the sharpest frames and stack those together. So that's what we did with Gemini. And the NIRI imager, when we're looking at this wavelength, we can't see the whole planet at once. The planet Jupiter was so big that we had to use 6 separate pointings. And then at each of these pointings, we take 38 images, we select about 10% the sharpest images, and stack those together to make the beautiful composite that you see in the press release. So here's the view that I promised. You can see the great red spot. Now these data were taken back in 2017 in January. And on the left, you see the Gemini 4.7 micron image. And in the middle on the right, you see Hubble images taken at just about the same time. And as I mentioned before, with Hubble, we're seeing sunlight reflected back from the planet. So we can view the visible wavelengths in the middle. It's roughly what the eye would see, although some contrast has been enhanced a little bit so we can see the detail. And on the right is ultraviolet, which is scattered back from actually the highest levels of the troposphere, where there's hazes and some of them absorb different ultraviolet wavelengths. So you see these crazy colors reconstructed from different UV filters. So Yeah, so here we have the simultaneous view with the great red spot on the planet. And this is the type of image that I'm capable of producing. This is, I made this image from the Gemini data and the Hubble data, but then I passed it on to the Gemini Public Information Office, and they made it even more appealing. So just so you can see the steps that they're taking to really make these images so spectacular, I'm really appreciative of the help that they're giving us with that. For the science, we can use my images, but just for visual impact, these processed images are just so spectacular. You can see all this detail. So on to the question, where does the lightning come from? So one of the things in these January observations, you can see a storm system right here in the Hubble data. This storm system, the counterpart in the Gemini data, you see a lot of dark material on a bright background. So the storm is pumping up a lot of cloud material into the atmosphere there. So we looked at this data set to study the storm, and the first results on this were described in De Potter et al. Paper. And the storm is really interesting in several different ways. The inset image that you see here is an image in blue light taken by Hubble, and you have the storm circled there. But if you were to unwrap Jupiter so you could see all 360 degrees of longitude, you notice that the storm seems to contain a series of pulses here. So this background image is in the methane band, where we're seeing these hazes, the same hazes that show up so spectacularly at ultraviolet wavelengths. But I've made little marks showing the longitude offset of these storm pulses. So in the middle of the storm pulses, you can see these bright areas that's really thick and high cloud particles. And in between, you see some dark areas. And those are areas where the hazes have been depleted, presumably by downwelling air. So there's a lot of upwards and downward motions in these storms. So here's a comprehensive look at that storm core. Now there's a lot going on here, so I'm going to spend some time to describe everything you see in these images. But on the left, you have Hubble information, and on the right, you have a map from Gemini. So as I said, you can see the storm is very cloudy, but the regions around it are bright at 5 microns that we see from Gemini, indicating clearings. Now in the Hubble data, I've used color coding here that shows the heights of the clouds, and the deepest clouds show up in red. So you can see in the middle of the storm here, there's some reddish clouds. And I'm claiming that these are water clouds. So we haven't detected the spectroscopic signatures that would confirm that they're water, but they're at such a high pressure, they're so deep in the atmosphere that we think these can't be composed of Jupiter's other exotic cloud materials, ammonia or ammonium hydrosulfide, that appear at the upper layers. So what else do we see in this image? You see some green and blue stripes here. These are the path of the Juno spacecraft overlaid on top of this map. So the whole point of this Gemini and Hubble observing campaign is we want to provide context for what Juno with its instruments sees. So Juno, let me show a little animation here. The Juno spacecraft is orbiting Jupiter every 53 days. And in fact, it's going to make a close approach just like this early next week. So the spacecraft on this 53-day orbit, it's usually, this is a very eccentric orbit. So it's usually, Jamika, do you have a question? I see you moving. Okay, well.
Yeah. We do have a question from our YouTube live audience.
Okay.
There are quite a few comments saying, hello, Dr. Wong, you have a lot of support out there.
Okay.
So our first question today is from Ian Wilcox. And Ian's question is the lightning on Jupiter different from lightning on Earth in any way?
Well, that is a very active area of research. So we're looking into that. I haven't told you what we found so far about the lightning, but by the end of this talk, I'll show one way that the lightning source regions are different. But there's a lot of work in progress trying to look at some of the differences between the Earth system and the Jupiter system. One obvious one is there's no ground. So the lightning that we're used to, there's a lot of cloud to ground lightning. So that's when electrical discharge connects the cloud to the surface. But there's also cloud to cloud lightning, and that's the only type that there can be on Jupiter. But the main similarity, we think, is that the lightning pretty much has to be generated by water cloud particles. And so if you look at my Hubble map here, that's why I think it's so significant that you see a reddish cloud in this cloud height, in this cloud height map. That reddish cloud is from the water level, so that's linking this activity to the substance water itself. So some of these little pink dots here are lightning measurements from Juno. So I want to explain how we get that information and how to interpret it related to this storm. So as Juno is passing by Jupiter on one of these close approaches, that's when it's sensing the atmosphere. And in this animation, you see kind of like a little searchlight spraying out from the spacecraft. That's meant to visualize the instrument field of view for the microwave radiometer, which is kind of the key instrument for looking at Jupiter's atmosphere and interior. Well, mainly at the atmosphere. So as the spacecraft is spinning, you can see that field of view is passing over this, this one spot. I can't use my laser pointer on top of the animation, but it's passing over this one spot and sampling it multiple times. And towards the end of this little animation, you can see that it's really viewing that spot not from a straight down angle like it is right now in the animation, but from a very oblique angle. And I think that's what happened in the map at the left. So the green stripe shows the path that Juno took as it was going, oops, let me go back here, as the spacecraft was going north to south. Now, the little pink circle marks a point on the planet every time a lightning spheric was detected. That's a burst of energy at radio wavelengths that the microwave radiometer was able to detect. And the pink dots show the exact pointing of the instrument at that time that one of these signals was detected. But in this animation, why don't I just pause it at the point that I'm talking about. You can see here, if the spacecraft was looking at that point, it's at a very, very oblique angle, and just a small error in the pointing, or actually a lightning signal that's coming off of the direct pointing, could generate some uncertainty in the positioning. So it's possible that all these strikes actually came from that storm. I'll just go back to the Gemini map here. Is there another question?
Yes, Dr. Wong, we do have more questions and comments from our YouTube Live audience.
Okay.
Our first comment is, wow, I had read about the heat from Jupiter, but I've never seen the IR spectrum from it like this. Beautiful. And here's our next question from Elizabeth Gregg. Elizabeth asks, how does Jupiter's magnetic field affect lightning?
Oh, so Okay, first of all, thank you for the first comment. But I can't take all the credit for Jupiter spectrum because what I'm showing here is imaging data. So spectroscopy is a very powerful technique that I'm not reporting on here, but that looks at different wavelengths of light. But here we're just looking at an image, so it's the brightness that's coming from different areas. The second question about the magnetic field is a very good question. I'm not sure if there's any understanding of how the magnetic field affects the lightning itself. But once a lightning flash occurs, signals from that pass through space and eventually get detected. So on previous missions, we detected lightning just from imaging experiments. A spacecraft imager was pointed at the dark side of the planet and you could see little flashes of lightning there. But here I'm reporting on radio signals. So those can pass to the spacecraft. And even with all the sunlight shining all over the planet, we still detect those radio signals. So that's one of the great advantages of Juno as a lightning investigator, is it's able to detect these signals any time of day, not just on the night side. So there's different types of radio signals. There's these spherics that I'm reporting here, and there's whistlers, which actually, once they leave the atmosphere, they're a different type of signal that actually follow along magnetic field lines. So they're a type of electromagnetic wave that will follow along a field line. So in that case, we don't look at where the instrument was pointed in space. We look at what magnetic field lines are mapping from the planet onto that spacecraft. So there's all different sorts of lightning signals, and some of those signals propagate under the influence of the magnetic field. But I want to move on from this storm picture here. So I just want to point out two more things of these maps. One is that the Hubble map was, as it says, it was taken 1.2 hours before Perijove. That's the Juno spacecraft pass. And the Gemini one was taken 21 hours before Perijove. So during that time, there's all these winds that are blowing east and west on Jupiter. They're sort of like these currents, alternating currents in the atmosphere. And so if you can imagine that as the Juno spacecraft was going over the planet, it was laying a series of green eggs on the planet. And then you go 20 hours back in time, those eggs would have been arrayed in a squiggly line as they are in the Gemini image. So we did that because we want to be able to compare the data and remove this effect of the winds blowing things around. And then the other thing I wanted to say is when you look at the Hubble image and the Gemini image together, there's a specific set of 3 different cloud structure properties that we see at this lightning source region. There's really thick high clouds. There's the deep water cloud that shows up red in the Hubble map that I talked about. And there's the clearings that show up so conspicuously in Gemini. They're very bright because the clouds have been cleared out. So, okay, I'm going to actually skip over this image. This is from the, well, I'll just quickly say that our investigation of this storm with the ALMA Observatory at millimeter wavelengths was sensitive to ammonia gas, and showing that these storm plumes are bringing up ammonia here. But if people have questions, I will come back to this image later. Jamika, more news from the channel?
Yes, Dr. Wong, we do have more comments and questions.
Okay.
This question is again from Elizabeth Gregg. And Elizabeth asks, where does the lightning go? Would it go really deep into Jupiter? Does it just dissipate? What happens to it?
Oh, I wish she had asked that question a couple months from now. There's a lot of exciting results that are going to come out about this. But basically, this lightning is happening inside the atmosphere. It's going it's cloud to cloud lightning. So it's happening within a storm. And there's basically just a lightning bolt inside a storm. So it doesn't actually strike any surface. It's just, you know, the way lightning is generated, there's an area of the storm that has a positive charge and an area of the storm that has a negative charge. And those two charges set up an electric field. And if those charges can accumulate, that electric field is going to get stronger and stronger until air, which is normally a good insulator, isn't able to stop that electricity. And then it goes, and you have your lightning discharge. So it just goes from wherever okay, I would have to do some reading on this. I think it goes from where the negative charge is to where the positive charge is. But there's all kinds of back and forth about how these ionized channels get created and then provide a conduit for that charge to get transferred.
Fantastic. Thank you, Dr. Wong. We will come back shortly with another question.
Okay. So I mentioned, when we looked at that big storm picture, I mentioned that there were 3 types of clouds present in that cluster of lightning strikes. So here we have a nice schematic that was prepared by the Space Telescope Science Institute to accompany their version of the May 7 press release. And this schematic shows all of these types of clouds that we saw. On the left, they drew in a convective tower. And what this is where the convection, the upwards and downwards motions that's transferring heat is most strong. And it's reaching really high up in the atmosphere. So you have thick clouds that reach a very high level in these convective towers. Another thing you have are deep water clouds. And these clouds are revealed by the Hubble imaging data because we have some filters that will cut off, just about right here where the word says Gemini thermal infrared. So in a filter like that, 727 nanometers, you're not going to see this deep water cloud. You can't see that deep. But in our other filter, we can see the deep water cloud. So that's how we can detect these clouds that show up red in those maps. And that's one of the 3 elements of this cloud structure that seems to be so important for convection. And then the third element, I said it before, clearing. And clearing is something that the Gemini data are really good at showing, these bright patches. And something that we said in the paper and in the press release is that it's kind of like a jack-o'-lantern. You have the deeper atmosphere with its heat is the candle inside the jack-o'-lantern. And wherever there's a clearing in the clouds, those are like the eyes or the mouth of the jack-o'-lantern. Okay, so that's this cloud structure, and we see it in another place. But Jamika, if you have another question, this would be a good stopping point.
Fantastic, Dr. Wong, you were right on time. We do have several more questions. We have 2 from our YouTube live audience. And the first one is, what would happen if an object entered the storm?
An object, okay. Well, that depends on how big the object was. The storm has objects in it. It has precipitation, so like hailstones and stuff like that. So there are objects in there. But if you're talking about something like an asteroid or a comet, like we saw with the Shoemaker-Levy 9 or the 2009 impact discovered by Anthony Wesley, you know, there have been impacts seen on Jupiter. So if something like that were to hit the storm, I have a feeling based on the size of those impact areas and the size of these storms, which, oh, there's a scale bar over here, 4,000 miles. So this scale bar here, 4,000 miles from the convective tower to the deep water cloud to the next cloud, that's the length along these little white transects that I've drawn through the maps here. So that's 4,000 miles. The impact scars from these incoming objects are typically smaller than this. So I have a feeling convection will continue to rage here. But what happens is with these impacts, you get a big debris field on top of it. So that would, all that storm activity would then become invisible to us. We just see a black smudge. Juno would still see lightning detection, lightning signals coming through at radio wavelengths.
Thank you. One more question before
Okay.
we let you continue, Dr. Wong. You're very popular today. And we also have some comments, which I will mention after this question. So Diana Greeton asks, she's wondering how are the clouds so neatly striped, and they're not poofy and swirly like the clouds that we see in our atmosphere, but they're kind of spread out. How's that happen?
I wonder about that. I think there's a lot of cloud textures that we are only beginning to see. And now I should have put some JunoCam images in this presentation, but it wasn't strongly related to this lightning question. Who was the questioner, Jamika?
The question is from Diana.
Diana. So Diana, I would suggest after this talk, Google JunoCam, JUNOCAM, and there are a lot of images that are kind of the highest resolution cloud images of Jupiter that we have from the JunoCam on Juno. And that camera was added to the Juno spacecraft to provide really public outreach imaging. So it wasn't designed as a science camera, but at the end they were like, we can't really go there and not take pictures of what it looks like. So they added it as a public outreach camera. And you can see a lot of cloud textures that don't quite show up in the Hubble images, or these Gemini images, you're seeing clearings in the cloud. So you can't really tell what the clouds look like. With the Hubble images, again, we don't have the resolution to really see some of the smallest cloud elements there, but there's things called pop-up clouds that have been showing up in the JunoCam data that look really cool. They're fluffy and fine-grained little clouds. But you're right, there are a lot of long stripy clouds, and the name of these regions. So I was going to get to this later, but if you see my laser pointer, these regions are very active in convection and lightning. And what I'm circling are cyclones that we call folded filamentary regions, or folded filamentary cyclones. And you're right, they have these textures that we don't really see on Earth. There's these long linear clouds, but they're kind of curved. And yeah, there is a lot of interesting cloud shapes on Jupiter. And we have explanations for some of them, but not all of them. So I showed the storm before that had a lot of lightning associated with it. And now here I want to show, let's see, I think I will. So, okay, take a look at this map. I'm going to zoom ahead a couple slides to where we see the lightning strikes. So here I'm showing them in blue instead of pink, but sorry, not strikes. There's no ground to strike. But these are the lightning radio signals, the spherics. And this cluster here is the largest cluster of lightning strikes that was seen in this paper by Brown et al. 2018, the first paper on Juno lightning detections, or part of a set of papers. So anyways, this is the largest cluster of lightning signals that was detected by the MWR. So we turned to our Hubble and Gemini maps to see what is causing these. What is the source region for this lightning? And it's up here. It's this folded filamentary region. And there's another one down here, which was the basis of that cloud schematic. We took a cut through here and showed the convective tower, the clearings, the deep water clouds, and the 4,000-mile length of this whole system. Okay, so let's look at how the Gemini data can tell us what's going on here. If I zoom into this map, I'm going to go step by step through some layers. So here's the cloud clearings are showing up bright in the Gemini data. Here's the Juno path for comparison. And again, there was a time offset. So instead of a straight line as the spacecraft actually traced, you see a squiggly path. And then here are the lightning detections. And I've drawn some boxes around these folded filamentary regions so that you can see there really is a connection between these and the lightning. Now, only 2 of these are showing lightning, but that's because Juno is sensitive to lightning that's near the spacecraft track. And the spacecraft track is here. So these folded filamentary regions off to the side, over to the west here, we weren't able to even sense lightning that far away. But all of these have a similar pattern in the Gemini data. They're mostly dark, that means mostly cloudy, but they have all these little blobs of bright stuff in the Gemini data showing little localized clearings. So there's vigorous up and down motions with the downwelling creating these clearings. You don't see lightning associated as much with regions that are just very cloudy, that don't have these vigorous up and down motions to create clearings. So this is kind of a new thing that we're finding from these studies. So, okay, this will be my last science slide. We got a little bit of a late start, but hopefully there's going to be time for enough questions. But I'm going back to this storm on the left, and on the right, we see super cyclonic storm Amphan, which just made landfall last week, causing $13 billion of damage in India and Bangladesh. But here we have some similar data to what we're looking at on Jupiter. So I just wanted to draw a little parallel here. It's been said in the press release that the Juno and ground-based observations that we're doing, it's sort of like having a weather satellite around Jupiter. Well, here we actually see some weather satellite data on Earth. And let's look at the layers in this image. So on the right, there's a black and white. That's a satellite, just a visible light image, showing that this, this tropical cyclone is very cloudy all over it. The blue to red colors, those are temperatures. So the red colors are the coldest temperatures, and that means you have cloud material and basically hailstones coming very high up in the atmosphere there. And the little black nuggets, those are individual lightning flashes that were detected also at radio wavelengths, but from a network of ground-based stations. And I think you can join this network if you have the right equipment. So I should look at this, but it's a WWLN Woolen network. And so I think it's includes a citizen science component. But basically, with a bunch of radio sensors on the ground, you can triangulate where the lightning is coming from. So a lot of these lightning signatures are associated with these very high clouds. So that's one of the similarities. Remember, we saw convective towers on Jupiter. But one of the differences is we found these clearings to be very important, or a strong indicator that you have this vigorous convection on Jupiter. But when you go back to the Earth image, it's cloudy everywhere. You don't see those clearings so much. So there does seem to be some differences here, and it's something that's going to give us years of puzzles to solve as we collect more data. And so I think, unfortunately, for next week's Parajove, we won't be observing with Gemini, but hopefully, as things come back online, we'll get more data and make more fabulous discoveries.
Thank you so much, Dr. Wong. We do have a few more questions and comments from our YouTube Live audience.
Okay, and I'm happy to stay a little bit late too, because, you know, since we got a late start.
We appreciate that. Thank you so much. And those of you in YouTube land, we appreciate you staying with us and being very patient, because this has been a fantastic presentation. Okay, let's continue with our next question. This one is from Ian Wilcox, and Ian asks, has the new Juno data revealed any new fun stuff about the core of the planet or its inner layers?
Yes, so the Juno mission, I'm really concerned and interested in the clouds. Lightning is a cloud process. This is the stuff that excites me, but that's only a small part of all the science that Juno's doing. Juno really has 3 key areas of science. magnetospheric investigation. Someone had a magnetic field question earlier. The atmosphere, which is what I've been talking about, and the interior, the core of the planet. So Juno investigates that with the gravity investigation. So basically, as the spacecraft is swooping by Jupiter, it's transmitting an ultra-stable radio signal back to the Earth. And by measuring that signal here on the ground, we can see little variations in the signal frequency that gives us the Doppler shift, basically, and can tell us about small gravitational perturbations. Over time, as the spacecraft keeps going by the planet, we build up a model of the interior, well, the gravitational field around the planet, which is controlled by the interior. So it's a long way of saying, yes, Juno is looking at that. And one of the interesting things is that it looks like the core may not be just like this solid ball there. It's kind of a fuzzy core that's maybe has gotten eroded over time or by some process. But this is something where there's not really a consensus. There's still ongoing analysis and different people with different models. So we hope to get the answer to that. The Juno data are really exceptional for providing a new look at this, but an eroded core is kind of one of the big new areas in that interior investigation.
Thank you. Another question. This one is from Ali Chen. And Ali asks, what type of precipitation would you expect on Jupiter, if any, during these storms versus the precipitation that we see on Earth?
Okay. So on Earth, well, I don't want to say Earth is boring because it's so exciting. We have drizzle, we have fog, we have hailstones, we have snow. So, and snow itself encompasses this whole range of like ice needles, ice columns, different types of snowflakes. So, so these are all things on the Earth that are caused by water. It's either water droplets or water ice particles. But on Jupiter, we have water. I showed those water clouds, but we also have ammonium hydrosulfide, which is so bizarre because it's not even, okay, I'll get back to that. It's really bizarre. But then we also have ammonia, which just forms its own ice. And we don't really have a lot of information about what those cloud particles are like. Ammonia, one paper said it could be tetrahedrons. Another paper said they could be, I forgot what it's called, prolate spheroids. So there's some uncertainty there about what these ammonia particles are shaped like. And there have been studies, especially with this great storm on Saturn, which, I mean, Saturn has a very similar atmosphere in some ways. In the great storm of Saturn, they detected spectroscopic signals of water ice, ammonia ice, and ammonium hydrosulfide all at the tops of the clouds. So you have this vigorous convection that's bringing up water, but on the way it's also collecting these other exotic ices. And so there's a much more diversity in terms of cloud particles on Jupiter. And that's only the pure cloud layers. There's probably interactions between these cloud layers. So in other words, a water droplet or ice particle, as it comes up, it could have ammonia freezing onto it, or it could have actual chemicals that are in between ammonia and water, hydrates. So there's a lot of chemical options on Jupiter that don't exist on the Earth.
We have one more question, if we have time, from our YouTube audience, and actually several comments. Let me start with this comment. This is a comment that is in reference to an earlier listener question. This is from Tom Jabal, an astronomer here at the International Gemini Observatory. And Tom's response is that he thinks the lightning mechanism is similar to Earth. The question was is the lightning different on Jupiter than Earth? And so Tom offered that it involves condensation and evaporation of water vapor in the clouds that are rising and falling in the storms. So thank you, Tom, for your comments. And we had a very interesting question as well, Dr. Wong, more of a comment and question from Carl Friedrich. Carl says he's interested in the intense auroras of Jupiter. Do the electrons react or stir up the atmosphere in any meaningful way, like lightning?
The electrons. So with the aurora, you have charged particles streaming into the polar atmosphere. And they're kind of stopped from getting down to the levels where the clouds I'm talking about are condensing and everything. So the auroral, actually, I shouldn't have turned off my screen sharing, because if I go back to I'm going to go back to the ultraviolet image, because this is okay. This is where we can see the aurora interacting with the atmosphere, maybe. So you have these charged particles coming in on the polar regions. And if I activate my laser pointer up here, and what do you see on the ultraviolet? You see the poles are very dark. And they have this weird color that you don't see anywhere else. Now the colors here, because I'm using 3 different ultraviolet wavelengths, this isn't real color, but it tells you that there's a certain ratio in the ultraviolet reflectivities here that's unique to the polar regions. So what these are hazes very high in the atmosphere, and they can be caused either by photochemistry or by these particles that are coming in, the same particles that create auroras. When there's auroral emission, it's atoms and molecules in an energetic state that are relaxing to a lower state and emitting light photons for us to see. But there's also chemistry, which is when those particles come in, they hit the atmosphere, and instead of just exciting it to a higher energy state, they'll cause different chemicals to form from the constituents present. And that can either come from these particles, or it can come from solar ultraviolet light that gets absorbed by the gases there. So it's not really clear exactly what is causing these hazes, and you can also look at spectroscopy to see some of these photochemical gases there, and their concentrations are higher at the poles than they are at the lower latitudes. So there's chemistry going on there, but again, these are up in the stratosphere, which is much higher altitudes than the clouds and convection that I talked about today.
Thank you so much, Dr. Wong. We have a few more comments in the YouTube live audience, but we will move it on back over to Odysseus to wrap things up. Those of you in our audience, continue sending in those questions, and I will make sure that Dr. Wong receives them.
Okay, thank you.
We're getting close to the end of our time today. So I want to say thank you again for joining us today, Mike. And thank you to all of our viewers and everyone who joined us in chat today. If you have any more questions, please find us on social media as @NOIRLab Astro. And we will see you here again next week with Jamika Marshall and Gemini scientist Tom Jabal, who I think Jamika mentioned is in the chat right now, talking about observations of the normally rare isotope of oxygen 18, found in some very unusual stars. So we hope you can join us at the same time next week. Aloha.